This conference will
Okay.
now be recorded.
I just wanted to say that Jeff Mann brings to us a whole lot of years of cryptography experience, having been a cryptanalyst with NSA, and just has a long line of technology and encryption knowledge behind him. He is, as you can see on his chart here, he is considered the InfoSec curmudgeon in the industry. And he has so graciously agreed to help us look at encryption specifically as it pertains to the way CISA would look at encryption because it is different. And he has agreed to put together this presentation and give us all a little talk about encryption. After his talk, we can give questions and answers. So if you have some questions that you want to ask him, feel free to. We'd love to be able to answer any questions you have. And we also want to give Paul Farrell an opportunity to tell us all the wonderful experience he just had in passing his exam. So with that said, Jeff, I'm turning it over to you.
All right, thanks, Sherry. Make sure I grab the right mouse here. That's me in case anybody has never seen me. And if you ever want to reach out to me or follow me on Twitter or call me, if I don't recognize the number, I won't answer, but that's the way things go. I thought what I'd do today is really quickly go through a history of cryptography or an evolution of cryptography. I find it helpful in me understanding cryptography, kind of understanding how it all started and how it's evolved. And hopefully that'll help things make sense. Because I think sometimes if we jump right into all the different things that are going on with computer-based cryptography these days, that it can get really overwhelming really quickly. So bear with me the first couple minutes. It's just going to be a whirlwind tour of about 2,000 years worth of cryptography. And then we'll bring it up to the present, and I will definitely defer to anybody that's been through the CISA exam to add color commentary to how CISA views cryptography, or maybe we can figure that out together. So really quickly, cryptography's been around for probably 2,000 years and then some, in the sense of very early on, ancient civilizations realized that sometimes they wanted to keep their messages secret. And you've probably heard of something called the Caesar cipher, going back to one of the Caesars in Roman times. And what Caesar did is figure out a way to scramble his messages by what's called simple substitution. And I can show you an example of that in terms of what it looks like in terms of cryptography. So this is just a couple slides I pulled out of some talks that I've given previously. What I want to show here, this is the preamble to the Constitution, in case anybody didn't know. And the way I, as a cryptographer back in the day, would look at a scrambled message would be to understand sort of the characteristics of the language. If you see here, I found this little cool tool somewhere on the internet. I don't even know what the link is, but I could probably find it again. You type in messages or cut and paste messages in, and it'll do a count of all the different letters. Stuff that we had to used to do back in the day by hand, and then early, some of the early computing statistical programs that we would use in the hallowed halls of where I used to work would automate this process. But we're going to do everything in terms of English for now, and the distribution of the English language roughly mirrors this. It's pretty easy to see that the most common letter is the letter E. In fact, the way I learned, the most common letters are what we used to call either the Etnorias letters, Etnorias, or sometimes we would call it senorita. Same letters. Senorita is perhaps more easy to remember, but Etnorias is in the order of frequency. So E and T are the most common letters. So if you take a simple substitution where you're taking basically one alphabet and writing it down, and then underneath it at some sort of offset, you're writing the same alphabet down, but A might start under the letter H, for example, and then you write A through Z and then come back around and finish it. This effectively scrambles the letters. So If you do a frequency count of this simple substitution, which, hint, it's still the preamble to the Constitution, now you see that the most common letter coming up is Y. So what we would do to try to break a cipher like this is to do the same type of count and then just do a guessing game and start filling in the blanks. So we notice that Y is the most common letter. And we intuitively know, since we sort of know what the underlying message is, we, the people, shows up and we start filling in and guessing the E's. When you do that, you take the second most common letter and so forth, and it's kind of a trial and error thing, and you look for patterns of words and words that you recognize. If the message happened to be in broken up by the length of the words, as this is, it's pretty simple to guess some of the smaller words. Like if there's a single letter word, it's either going to be an A or an I, and so on and so forth. And you keep filling in the letters until you recognize words, and through trial and error, it's pretty easy to break the message back to the plain text. If you've ever done those little crypto puzzles in like airport magazines, or if you're old enough to remember this thing called a newspaper and the comics pages, very often they would have puzzles like that in there, and that's kind of what this is. The way that you would break ciphers, as I was saying, is you're looking for patterns, you're looking for the frequencies. Later on, there's other methods, and there's methods that I can't really go into a whole lot, but if you Google them, they're probably not terribly as secret as I think they are. But there's a lot of different ways, sort of, and this is the essence of cryptanalysis, which is the breaking of codes or breaking of ciphers. We'll slide on real quickly. Another form of cryptography, at least in the classical sense, besides ciphers, is something that's called codes. In the old days, they were something completely different. Nowadays, I hear these words sort of used intermittently, especially in terms of modern cryptography. Not sure that the terms are accurately used all the time. Most people just sort of use these synonymously, but a code essentially was another way of hiding a message, but it was more often done by exchanging words and phrases rather than simply a letter for letter type of substitution. I did a talk recently where I was talking about the history of cryptography back in the American Revolutionary times, and learned about this group that was called the Culpeper Spy Ring. And in fact, somebody hearing the talk informed me that there was a series on I forget who originally aired it, but it's on Netflix now, and the series is called Turn, and it's the stories of Washington spies. So this is an actual spy ring that operated during the American Revolution, and this is an example of the code book that they used, where they had a series of words written down with numbers substituting for them. In modern terms, this is sort of relates to what we hear these days in terms of tokenization, where there's a value that is associated with a specific underlying value, but supposedly no relation. The code for all the different players that were involved in the spy ring, each player, they had a in most cases a separate name, and then they had a number assigned. So Agent 711, according to this code list, happened to be George Washington. So that's an example of a code. Now, codes were somewhat harder to break, especially, and essentially the way you broke them was you figured out the frequency of the numbers and you started guessing what the things might mean, or you basically got a hold of a copy of the code and then you could read everything. Ciphers in particular, no matter how complicated, and there's many versions of ciphers that do substitutions, but they essentially, in their attempts to disguise like the frequency of the language, the frequency of the letters and words, there's lots of different ways that they could all be broken. But what changed everything sort of in the evolution of cryptography was applying some sort of stream of random characters that would help to suppress the characteristics and make it harder to break. What I used to use, what I was most familiar with back when I was working for the DoD, was something called the one-time pad. In essence, the one-time pad assuming that nobody steals the pad, gets a copy of the pad, and in particular pays attention to the name one time and only uses it once, it actually is unbreakable. There is no mathematical, computational, cryptanalytical way to break a message that's encrypted using a one-time pad. The ones that I used to use very frequently, or my customers, as you were used to use, used a method that combined the alphabet with a reverse of the alphabet in 26 different offsets. And it would produce, if you go down row and across the column, I said that wrong. If you go down the column, go across the row, find two letters. One might be the plain text letter of the message. One would be the key, which is the letter that's shown on the one-time pad. You sort of connect them in the middle. You get a third letter, and that is your cipher letter. That's the letter you would write down and end up sending a message. The three letters are unique. No matter what order you put them into this table, you get the same result. Any two letters leads to the third unique letter. Real quickly, I'll just show what this looks like, just because I had fun playing with these slides a while back. So you write a message out. Typically, the first 5 characters were left blank, and that would be the call sign, if you will, or the indicator of the person receiving the message to know which page of the one-time pad he was supposed to use. In theory, it would be the next page because you use it once and destroy it, but sometimes messages might get delayed and they might come in out of order. So you write your letters one for one, and you go through that Vigenere table and you write down the third letter as a substitute, and that in red is the message that you would send. So you get the message, you reverse it, and same process, you get back to the end of the message. What that does effectively, and this is a similar type of count of the letters in a message that was put through a one-time pad, it eliminates any of the characteristics of the underlying plain text, the English language. So, even though G in this table looks like the letter E, chances are it wasn't. In fact, there's no way to prove it. It could really be any letter. So in the evolution of things, that was called paper systems, or when I was working in an office in NSA, it was called the offline or manual crypto system shop. So next in the evolution was we started building machines. And does anybody recognize what this machine is? I guess if you're all muted, you're not going to shout it out. This is the Enigma machine. And it was used in World War II by the Germans and used actually for many years after that. Quick trivia question or point of trivia is when I started working for NSA, which was in 1986, the fact that the Enigma machine had been broken by the US and by its allies was still secret. And it was because it was still being used by certain lower level countries, Soviet bloc countries that were doing lower level, less important communications. I find this fascinating because the Enigma machine was broken back in the 30s, and it was used by some people thinking that they had secure communications on up through the 80s, probably a good 50 years. That is an example of how important it is to keep secret the fact that you know how to break things, which is kind of a lost art. So with machine cryptography and the need to primarily encrypt communications, messages that you're trying to send, think military, think government, think State Department, think those types of things. The way I learned it, there was 3 different ways that you did that. One is called offline encryption, where you encrypt the message before you send it. Like the message that would be encrypted on a one-time pad, once it was encrypted, it didn't really matter how you got it to the other person. You could write it on a piece of paper and somehow get it to them. You could, and most of the communications back when I was there was over radio of some sort. It could be sent by Morse code. It could be sent in a message where somebody's simply reading the characters, anything like that. But the point is, the message was encrypted before it was ever sent. The next sort of evolution of that was something that was called inline secure communications. And what happened there was that in NSA, this is what we used to do, at least on the InfoSec side of the house, was build little black boxes where the message would go in, some sort of crypto algorithm would be applied, and out the other end there would be a message, a code, a cipher, what we used to call the ciphertext, and that could then be sent out, with radios or whatever the communication method was. And then finally, ultimately, there's what was called online encryption, which essentially meant there wasn't any like little separate device. It was whatever the system or device was that was transmitting the cipher, the crypto was going on within that system or that application, sort of in near real time. And this translated mostly to voice communications, where somebody's talking and the voice signal would be converted to an encrypted signal sent to the other end, decrypted, and hopefully you would hear the message as someone's voice on the other end. So, just real quickly, these are just some examples of systems that were in use back when I was with the DoD. So that's a lightning fast history of cryptography that gets us up to computer-based cryptography. And probably the best thing to remember or take away from computer cryptography is it's all being done, in code of some sort within an application or a function or a procedure. It's all being done in the computer. Very often it's done in memory of the computer. Sometimes it's done in what has come to be known as firmware, which might be a special chip that's in the computer or in the device. And supposedly and hopefully that's protected from physical tampering. It's protected from breaking into the system and then getting access to that device. But the way the cryptography kind of works in computer times, and this is by no means a complete list, but I think what we're most familiar with or where we encounter encryption and cryptography these days is in the use of passwords and keeping passwords protected and secret. Certainly in protecting data, both being stored within computers or database or files, as well as transmitting or communicating the data. Communications themselves, the way the computers talk to each other, the way the computers talk over networks, and so on and so forth. Data integrity, is the data that you're receiving real? Is it accurate? Is it the information that the sender intended for you to get? It hasn't been altered in some way. And kind of a new thing, which is called non-repudiation, which is, I'm going to blank on the definition right now, but it has to do with verifying not necessarily what the content of the data is, but knowing that it came from who you intended it to come from. And when you receive it, you have to say that you received it, that type of thing. Not necessarily technically cryptography, but is sort of an application of cryptography in computer terms. To put this in more familiar language, some of the terms that we're more familiar with, and especially that have been issues, particularly within PCI the last couple of years, things like the use of encrypted channels rather than clear text communication channels, things like VPNs, secure shell, IPsec. I could have thrown up here FTP-S or secure FTP, secure file transfer. Our favorite one. That's true, Jeff. It doesn't imply encrypted. Thanks for correcting me. SSL and TLS as protocols or methods of doing encrypted communications. In terms of data encryption, we think of database encryption, encrypted data sets within databases. There's file encryption, there's disk encryption, there's email encryption, and so on and so forth. And in terms of the types of encryption, very often it boils down to it's either done in software, it's done in the application, or as I said, it might be done in firmware, which is would be considered hardware-based. What's come about very often now is hardware security modules or HSMs, which is an example of a hardware-based type of technology. And then the things that sort of get to the data integrity, things like the authentication, where you have things like checksums and hashes, which are Not technically encryption, but they're using some sort of mathematical or cryptographic algorithm that you put a set of data, or you put characteristics about a set of data, a file, through this function, and the output that comes out is intended to be unique for that file, and if that, or data set, if you will. And if anybody tries to alter the data, if anybody tries to modify the data in any way, it would produce the different characteristics that when you run through the hashing function or the checksum, it would produce a different output and would be an indicator that somebody's messed with it. The early uses of checksums and hashes were to try to detect if bad guys, hackers, had broken into systems and installed things that are commonly called rootkits, which would very often be modifications of regular system files and system commands that everybody uses that would have, let's say, hidden features or unintended or unpublished features that the hacker could take advantage of. Roughly speaking, when it comes to data security, and this has been true for quite a long time and is still true today, there's three aspects to data security. Confidentiality being one. This is the CIA, which you've probably all heard about. The idea of keeping the data secret, making sure that nobody can read the data, that it only gets to the intended recipient, that only people that are authorized or supposed to be reading it can read it. Data integrity then is making sure that the data is real and that it hasn't been altered. And availability, which is sort of a nuisance in some ways, but a very common problem in terms of modern computing and networking, is the whole idea of availability. Is the data available? Can we conduct commerce? Can we do things? Does the data go through and get to the destination? So that brings us then to hopefully a discussion that's a little bit more related to the CISA training, and this is where I'm sort of taking a little bit of a shot in the dark, having never been through CISA training, but let's give it a whirl. I've used this slide many times to try to explain how cryptography works to people, and people seem to love it, so I thought I would share it with you. Most of our discussions and the questions that we'll have in the Q&A time, hopefully we can come back to this and use this as a guide. But very simply, the idea of encryption is taking something that's readable, some sort of data that anybody can read, doing some sort of math stuff to it, an algorithm, some sort of cryptographic algorithm, and using that in conjunction with a key, some sort of stream of random, produces a cipher that hopefully can't be intercepted and broken or read by any unintended recipient. And there are two basic types of encryption that happens in computer-based communications these days. The first is what's commonly, or I guess scientifically, referred to as symmetric key. And that simply means that, in terms of this weird math function, the key that's used is the same key on both ends. So both the sender and the recipient somehow have a copy of the same key, so that they can apply it to the math function, the algorithm that they both have possession of. It might be an application, it might be a function, it might be built into whatever they're using, but they can use it. They both have a copy of the key, and they can encrypt and decrypt. They can send the message securely and then read it on the other end. That's symmetric key cryptography. The second one, which has really what sort of revolutionized the ability for people to do the mass communications and fast, speedy, transparent type of secure communications over the internet, over networks, is what's known as public key cryptography, or more simply asymmetric. And what this simply means is that rather than one key that works in both directions, each ends of the communications, the sender and technically the recipient, but he, in terms of this, he's listed as the second sender because he's going to talk back. They each have what's called a pair of keys. One is considered public and one is considered private. As the name implies, the private key is held by the owner of that key. So sender 1 has private key 1, and he keeps that. And public key 1 is what's sent out and is available to anybody that wants to communicate with that person. And conversely, then sender 2 has the similar set of key pairs, only in reverse. He has his own private key that's held and a public key that's sent out. The way this works most often is if we go to any kind of encrypted website, any HTTPS site, this is coming into play. Initially, the public key that's sent out is what's, in terms of web traffic, is more commonly referred to as a certificate. There's some minor differences, but effectively it's the public key. And when a web session is enabled, when you try to connect to a secure site over HTTPS, there's a key exchange. The public key is taken, and there's an initiation of a session where the public keys are exchanged, and between the two, then there's what gets sent with the asymmetric cryptography is what becomes the symmetric key that is used to enable the communications. So by using this method, you don't have to figure out what your symmetric key is and send it out to all the different websites or all the different customers that might want to connect to you on the website. So ultimately, the session is being done symmetrically with a key that's unique for that session and is used fast, because symmetric key cryptography, in terms of doing the calculations, the math, the algorithm, whole lot faster than doing this continuous stream of key exchanges with taking the public key, sending some data, receiving it, sending some data back, going back and forth, trying to agree on things. Sometimes that's called a handshake. So as you can imagine, and I'm going fast and I'm going very high level, but I'm hoping just to try to give you guys an understanding conceptually of what's going on here. As you can imagine, in terms of cryptography and keeping these communications secure at all levels, the key is the key. And what that translates to, and these are terms that I think are in your course material, things that you should be familiar with. There's certainly things that come up in the PCI data security standard. And the whole concept is, how do you keep the keys private? How do you keep the keys secret? How do you keep the keys from leaking out to unintended recipients, the bad guys, people that are trying to steal the underlying data? So overall, the methods of protecting the keys is called key management. That's sort of the sort of overarching term. One of the elements then is key strength, how long the key is, and in computer terms, the keys can be thousands of bytes long or bits long, and thanks to the computing power that now exists, it enables the keys to be really, really large. So in terms of the cryptography, in terms of the algorithms, you're doing things at the speed of computers that mere humans can't keep up with. Key distribution then is the way that you are able to put the keys in the hands of both ends of the communication, both the sender and the recipient. And the way that you get, presumably the sender is the one that's creating the keys, and he wants to communicate to, some other party. He's got to get the key, if it's a symmetric key, to that other end. So that is key distribution, and the ways to do that in a secure manner. Key integrity, as the name implies, it's assuring that the keys themselves haven't been tampered with, haven't been altered in some way, haven't been substituted by somebody else's key in some way, so that an unintended recipient is then receiving the messages. And then somewhere along the line, the keys get to both ends, and they have to be stored somehow so that they can be used when the time comes, but they have to be stored in a secure manner. And so there's terminology that comes about in terms of one of the methods of protecting keys is to encrypt the keys themselves using some other algorithm, some other math function with some other key, and that's often called the key encryption key. So in modern computing terms, you might hear reference to the data encryption key, which is the main key we're talking about. And sometimes you'll hear about a key encryption key, which is the key that's used to encrypt the data key that's ultimately going to be used. And there's different ways that each of those types of keys need to be stored and need to be protected. What I thought I'd do now is, Sherry had sent me, I guess, the ebook that you guys are using, and I wanted to, what I did was I just pulled out sort of the glossary of terms, because my guess is, and those that have taken the CISA exam can confirm this or not, that you're probably going to be quizzed or tested on at least some of this terminology. So I wanted to just run through this real briefly, and then I'm happy to take questions, and I'm more than happy to hear from the people that have actually gone through the CISA exam to see what their experience was in terms of the level of detail that the exam's looking for. So very quickly, I think I've covered many of these terms. Plain text is the plain data, the English, the message that hasn't had anything done with, that can be read by humans or read by machines or applications and acted upon. Ciphertext is what happens after the cryptography happens, after the encryption. Encryption is the process then of producing ciphertext that we've described is using some sort of math or algorithm along with a key that produces ciphertext result. Is anybody else hearing like a busy signal?
Uh-oh, yes. There we go.
Somebody, I don't know. How to stop that. Should I talk over it?
Sean? It may be Sean.
It looks like it's Sean. Oh,
there we go.
I just muted him.
Thank you. A hash function, as I said, a hash function is sort of a one-way math function. It's not reversible. I think Jeff Hall had pointed that out. A hash function is a one-way function. The most common early use of hashes beyond checksums in determining file integrity is in the use of passwords. When we type in a password to a system, whether it's a Unix password or a Windows password, I can't vouch for all the applications that we log into, but typically the passwords run through this one-way function to produce a value, and that value is then stored, hopefully in a protected manner. So that when you type in your password to log into something, the password goes through the same hash function, the same math function algorithm, and the output is simply compared to what's listed or what's on file for being your password. There is no lookup, there is no decryption, there's no breaking of passwords. It's simply a comparison. Does the result of the hash function match what you have? And if it does, you've got the right password. So all the password cracking tools that are out there are attempts to try to guess the password. Hopefully you know what the algorithm, the hash function is that's used, with whatever variations and different key streams that get applied to it to make it stronger. But the output on the other end is what you're trying to match ultimately. A message digest, they have it listed. I don't think this term is used very often, but basically it's the output of the hash function. Very typically, hashes are a specific size, what they call a block. It's a block of data that goes through the hash function and produces a block of data of a particular size. Digital signature is a method of sort of applying a little bit more to the message to try to personalize it, to try to say that this is uniquely a particular person's message or a particular person's key in terms of exchanging public keys. It's a little bit extra that's added that's just intended to be unique to an individual. Algorithm is just the generic term for the math. it sounds fancy, but it's a math problem basically at the end of the day. Decryption is taking the ciphertext and converting it back to plain text. Cryptanalysis then is the science of trying to break the cryptography to get somebody that isn't the intended recipient to figure out what the underlying message is. It's important to point out, I think, that finding what's considered to be a cryptographic attack against most of these algorithms and encryption systems that are used today, especially in computing terms, cryptographic attacks are very rare. A cryptographic attack, by definition, at least when I was working for the DoD, was any method that would reduce the work factor, how long it would take to break an encryption system, reducing it by 10%. In saying that, I should point out that all these systems, because they have sort of finite elements to them in terms of what the algorithm is and what the key that's applied, even though they might be thousands and thousands of bits and bytes, they're all mathematically solvable simply by trying every possible combination, what's called brute force, trying all combinations. So the easiest way for me to understand it and hopefully to explain it is, again, thinking of passwords. We talk about, in PCI terms, the need for a 7-character password. And those 7 characters can basically be, in most cases, any key on your keyboard. So uppercase letters, which there's 26 of them, lowercase characters, there's 26 of them, all the digits, another 10, and depending on the keyboard and the system, another 10, 15, 20 special characters. All those characters are possible for each position. And so when you do the math of how many possible combinations are, you get very large numbers. To reduce that in any way, like let's say somebody's typing in a 7-character password and they do scientific study, they do surveys and analysis, and they discover that 90% of the time people will start a password with either a capital letter or the number 1, let's say. Instead of the 80 or 90 possibilities for that first character, you're now down to 36 or 40. Or conversely, let's say, statistically, by people doing surveys, they determine that everybody ends their 7-character password with an exclamation point. Again, that last character, if you can assume that you know what it is, you've reduced that work factor by 1 place. So something to the power of 7 now becomes something to the power of 6, which mathematically is a much smaller number. That doesn't happen very often in terms of modern cryptography. What more often happens is somebody figures out a way to brute force more efficiently. A great example is I don't know how many years ago it was, there used to be an algorithm called the Digital Encryption System, or I think that's what it stood for, DES, the DES algorithm. It had 40 bits in terms of its key length. And some people figured out how to basically break the calculations up into small chunks, and they found ways to distribute the calculations over multiple computer systems all over the internet. So what would have taken one computer, and I'm making the number up, let's say 10 years to try all combinations to brute force it, by spreading it out over dozens or hundreds of machines, they reduced the time it took to brute force it significantly enough that it was able to break it. And I use, breaking it is a misnomer. They were able to solve the brute force because they were able to distribute it. Something like that is more common, or simply finding ways to steal the key, or finding ways to interfere with the normal operation of the encryption so that it's not really happening. These types of things are more common in terms of cryptanalysis. Encryption key, we've talked about that. The key encrypting key, we've talked about that. Key length, we've talked about that. A couple more things. Block cipher is a cipher that's encrypted basically in chunks at a time. You know, and it's done, this sort of goes back to what I remember as being inline, which I don't think technically exists anymore, but you take a chunk of data, you encrypt it, you send it. You take another chunk of data, you encrypt it, you send it. And that's different from stream cipher, which I used to call online encryption, which is sort of happening in real time. It goes in and goes out, goes in and goes out, and gets sent on its way. An initialization vector, an IV, is basically finding, in the old days, especially with machine cryptography, the cryptographic keys that were generated were finite. They might be huge, but they were finite, and very often they would repeat. So think of it as a big circle of data, and picking a point somewhere on that big circle of data is your starting point. How you get to that particular point and how you get the person on the other end to start at the same particular point would be called something like an initialization vector. We've talked about symmetric encryption. That's when there's one key involved. Asymmetric or public key cryptography, we've talked about that. Key exchange is the way you get the keys back and forth, which again, most commonly in computing terms is web traffic, where the key exchange initially for like having a secure web session is done with the public key cryptography that exchanges what is effectively the symmetric key that's used for the bulk of the session, and that's done with the initial exchange using the certificates, which are essentially the public key, to create a way to securely send the encryption key to both ends so that they both use it for the session. Digital certificates, we've talked about that. Those are effectively the asymmetric public key, again, oversimplified. Certificate authorities, these are sort of places that create these certificates and vouch for them. They validate them. They're a trusted source that you know that they are essentially built according to a specification that they will be able to be used for all the systems that you're using them for. And a registration authority then is where you can register them for public use. You can imagine that your laptop does not hold the public key for the 500 million websites that you might be able to visit. They're typically held in registration authorities so that when you're connecting to a website, they go and get the public key and they start the process. I got one more. Certificate revocation list is lists of bad certificates, bad for whatever reason. They've been compromised. They've been known to have been stolen or tampered or altered in some way, shape, or form. You can read all those words there. And I don't know what a certification practice statement is. I'm going to read it too because I don't know what that is. But anyway, I think that's the last of those slides. So hopefully I haven't confused you. Hopefully I've illuminated a few things, and I would be happy to take questions, and I would be even happier if somebody that's been through CISA could jump in as appropriate for any questions that might be asked.
It's been a few months since I took it. There's some public and public key questions.
Do you have, you're probably not allowed to share what the questions were, but are you able to sort of discuss the nature of the questions?
To be honest, I mean, I took it back in September. I'm not really sure I remember that far back, but I just, definitely there was, there's some questions related to the material you just covered.
Okay.
I don't know if Paul if Paul feels comfortable shedding any light on that, since he sat the test on Tuesday and passed it.
Well, I guess, I don't want to violate ISACA's NDA, but I will say that in general, I thought the test review question book that we've been using, Clark, was pretty good and accurate. And in the test review question book, if you guys remember from last week's book club session, there were questions about the specific mechanics of how digital signing works and how certificate authorities work and how PKI infrastructure works, like practical applications. And I think that's pretty important to understand for the exam.
Yeah, and going a little wider on that too, we just had Mark and I had a conversation that turned into an hour-long conversation on this topic with a client about how they were protecting keys, and it was really clear. There's a kind of a newer requirement that talks about, they need to document their encryption architecture. And, this was a very large client, and it was pretty clear that even, those folks didn't have that good of a grasp on this stuff, which was a bit scary.
I always think it's funny because I've done this similar type training for the online book club back when it was CISSP focused. And, back then I think I emphasized, look, the book has all sorts of details and minutia about the names of the different algorithms and what makes them all special and unique. And as you said, the details of how certificate authorities work and PKI. My sense is that they like to ask questions like that because that's where there's some detail in it. But for all intents and purposes, as a practical matter, I don't think you need to know that stuff like to live your life. But, so I can only encourage you to, memorize the course material because that seems to be what's necessary for so many of these certification exams. I try to stress, like, well, what does it mean out in the real world and what does it look like? And most of this stuff is frankly transparent to the typical user. Maybe we could shift a little bit and talk about, and hopefully this is what CISA tries to drive towards, is like when you're going in like to do a PCI assessment, and you're stumbling over the things that relate to requirement 3, protecting data at rest, or requirement 4, protecting card data in transit, or the things that talk about use strong cryptography for communications, or use strong cryptography as they pertain to passwords. What are the types of things that, well, I guess without violating the non-disclosure, do they touch on that at all, even in a remote manner on the exam? Or, what do we think we need to look for in terms of, well, how do I know if they said that they're using a particular algorithm, let's say triple DES, or they're using AES 256, how do I know? Or I know one of the things that we've been debating, not recently, but in the last couple months, is the use of particular hashing functions like SHA-1 or 2 or 3. Any questions or comments on that element of things?
Well, SHA-1 should never be used anymore. I mean, you can use it to create a message signature, to prove that the message is the message, but I would not use it as a hashing function. There are just too many holes to it. SHA-2 is still accepted by NIST, but NIST tells people stay away from it. And SHA-3 is the new one, and it's supposed to be where everybody's supposed to head.
Well, I have a question for you, Mr. Guru. In making those statements, are you implying at any time that a hashing function of whatever size or whatever flavor can be used for long-term storage of cardholder data?
Well, a hash is a one-way function, so it does convert the data to non-CHD.
Right.
So once you've hashed it, it's no longer cardholder data.
So you don't need to protect it or store it in a secure manner.
Nope.
Like, say, a password file that has a bunch of password hashes.
Right, but here again, this goes to what Jeff was talking about. Typically, when hashing is done, the algorithm adds not just the hash function, but a salt to it, which is just a large number that gets ANDed or ORed into the computation of the algorithm and creates an even more bizarre answer that comes out the back end.
Right.
So SHA-1 in and of itself is not secure, but SHA-1 with a salt of a certain length, and it escapes me at the moment. I want to say 128 bits, but it might be larger than that. That does make SHA-1 supposedly secure as a hash. So you'd have to ask the client, and this is where it gets tricky, because 9 times out of 10, if you say, well, you're using SHA-1, are you salting that hash? And they'll stare at you like, huh? What did you just ask me?
Yeah, which usually means either they're not using one, or let's say they've got multiple point of sale systems where they're using hashing functions and they are using a salt. Chances are they're using the same salt all over the place. And I'm
Oh,
not
of
sure.
course.
And at the end of the day, that doesn't add a whole lot of value either.
Well, it depends on who set the salt value and where. Because remember, again, you would have to find that salt value in there, and sometimes you can't find it because of the way the vendor has loaded up stuff.
Yeah, they probably don't know where it is either.
No. And this, it's the same discussion with programmers. They code now at such a high level, they don't know what's going on. Encryption is almost the same discussion, unfortunately, because I load a library that does the encryption. I don't know how it works. I just call this and it works.
Right. One thing I find interesting, and this will be sort of a soapbox moment, when I was working for the DoD and NSA specifically, back in those days was sort of the one-stop shop for cryptography and cryptographic solutions, secure communication solutions. I used to work for a time for the part of the organization that would evaluate the systems that we had created and put in the field. Or we were designing new systems. And the rule of thumb that we always followed was assume that the adversary knows everything about the math, the algorithms that are in our system that we're building. They've probably stolen a copy of the system. They've torn it apart. They've broken it apart. And put it back together. They know completely how it works. They have all the instruction manuals and maintenance guides. They've got everything that they need to know about the system. And our job was still to make it secure, and secure as long as it needed to be, what it was being designed for. And the way that was done, it focused almost entirely on the key and protecting the key and making sure that the key couldn't be compromised. And when I first started coming out into the private sector, and in particular in the beginnings of PCI, where the encryption requirements have always been there, but 15 years ago there were very few commercially available solutions for encrypting data at rest, let's say. I always thought, wow, it's really hard for governments, or what we call nation states these days, to do cryptography well and do it securely. How is the private sector, how are commercial companies ever going to do it? And one of the ways that they do it, and it may just be me, but very often if you ask a vendor, as Jeff's saying, they don't always know what's happening, but very often, even if they do, they're not going to tell you. They fall on it. They fall back on, well, it's secret, it's proprietary, and they put strength and value in keeping a secret their methods, which to me is never, doesn't make sense. That doesn't fly. Yet that seems to have become the norm in the, because so many people don't really understand what's going on.
Well, and from your history aspect, Jeff, all the good algorithms, interestingly enough, a lot of them were generated by Russian mathematicians back in the day. They just didn't have the computer power to prove them out.
Right.
So a lot of what a lot of what gets done came out of public mathematic papers published by the Russians, taken and effectively weaponized by the US and other Western states.
Sure. All right. Any other questions? We're coming up to the top of the hour.
Everyone's being very quiet. I think that, Jeff, we really appreciate you coming and speaking to us today. Thank you so much. I know I learned a few things here and there with it, and hopefully everyone else did too. If nothing else, we know you're a little older than we thought you were.
Yeah, some people think some people think I broke the original Caesar cipher, but I disavow that. So if you take away one lesson today, it's if you really truly want to protect something, use a one-time pad.
There you go. Thank you, Jeff, for your time today.
All right, sure.
Thank you, guys. Really appreciate it.
Not a problem. Hope everybody passes their exam.
Thank you, Jeff.
Thanks.
Bye.